Hi everyone, I'm Deepak. Today I'll be talking about our research homogenizing non-IID datasets via in-distribution knowledge distillation for decentralized learning. This paper has been accepted at the Transactions on Machine Learning Research. Let's briefly look at the deep learning pipeline. Data is collected from various sources which can be labeled or unlabeled. To this data, pre-processing is applied and is used to train a deep neural network. Once trained, the model is deployed and monitored continuously. In this pipeline, we focus on the dataset and training aspect in our work. There are many aspects of the dataset that reduce performance. In this work, we specifically focus on one problem, which is the dataset skew. When the dataset has non-IID distribution, this results in dataset skew. For example, consider a dataset of cats and dogs with 1,000,000 cat images and only 10 dog images. This class imbalance results in skew. This is of particular interest in decentralized learning, where such skew can result in large drop in performance. Let's quickly discuss the setup for decentralized learning. Decentralized learning distributes the training process among many compute nodes, seen as N0 to N5 in the image. Each node works on a subset of the data, allowing for the use of large models and huge datasets. These local datasets are called private sets, as they're not shared with the other nodes. During training, each node communicates gradients or model parameters with its neighbors. This is used to learn a global consensus model using its local updates and also from its neighbors. There are many advantages of decentralized learning. Firstly, robustness. Since there are many nodes and there is no single point of failure, the whole system is more robust to failures. Privacy. Since the data stays local and is not shared among the nodes, privacy is maintained. Next, there is speed up in training. This is achieved either through data parallel, which distributes the data among the nodes, or model parallel, which distributes the model. In this work, we've considered the data parallel setting. While there are many advantages, there are some disadvantages or problems with decentralized learning. Primarily, it's due to lower performance under certain conditions. One such condition being dataset skew that we discussed about. The other reason being the connectivity of the nodes. Less connected topologies lead to slow speed of information travel and hence reduced performance of the global consensus model. In this work, we focus on addressing the performance drop from dataset skew. We show the dataset skew on screen with more skew as we move from left to right. In each image, the x-axis denotes the class and the y-axis the node number. The size of the circle visualizes the number of examples in each class. Hence, as we reduce the direct lead parameter alpha, the skew increases. So what's the solution to reduce dataset skew and improve our performance? Maybe we reduce dataset skew in the simplest possible way by exchanging data. But this results in privacy being compromised, so that's a no-go. Maybe we can exchange public data instead of private data. Well, that's a good idea. So let's try it out and see what happens. Well, if I'm looking at this right, when we exchange data, we see drop in performance. This is very counterintuitive. Why is this happening? Why is the naive solution giving us lower performance? When we looked into it, we saw there were actually two problems that results in lower performance. The first we call label conflicts. So what is happening when we learn with public data being exchanged? Firstly, each node trains on its own data for a little bit, then labels the public data using the model that's locally learned. The labels for the public data are then exchanged, and each model updates and fine-tunes its models based on its own private data and the public data labeled by its neighbors. This is where the problem comes from. Let's say we have two different nodes. Consider node 1 and node 2 in the image. And let's say the sample is very close to the decision boundary. So one node, in this case node 1, may label it as class hexagon, but node 2 might call it plus square. So the same image has conflicting labels from its neighbors. So we need a way to handle this. Secondly, there is dataset misalignment. When we're using public data, we're effectively sampling the latent space. But sometimes if the private set and the public set are not well aligned, the public set may sample in regions which don't have support in the private set. Thus might not do a good job in communicating some of the decision boundaries learned by model A to its neighbors. Thus, to address the problems that we previously discussed, in this paper, we propose in-distribution knowledge distillation. It addresses both the label conflict and dataset misalignment problem. We use two ideas. Firstly, we use an OOD detector. This reduces the alignment mismatch between the public and private dataset, but also reduces label conflicts. The second idea is we implement a majority voting strategy to alleviate any remaining label conflicts. The first step of IDKD is to pick a baseline algorithm, such as DSGD or QGDSGD-MM, and train it to near convergence. The next step of IDKD is to take the public dataset and generate soft labels. Soft labels are labels with not just class information, but also probability information. Next, we perform OOD detection on the public images, after which the soft labels generated on these public images are exchanged with the neighbors. We take the labels from our neighbors and use it to fine-tune the local model. Next, we repeat steps 2 to 5, which is generate soft labels, perform OOD detection and exchange these labels, and fine-tune until convergence. Let's look at the performance results of IDKD. Here we present the results on CFAR 10 and CFAR 100 datasets. These were obtained on a ring of 16 nodes when the alpha parameter, the skew parameter, was set to 0.05. This is very high skew. As reference, we also provide centralized SGD results. This represents the upper limit of performance for any decentralized setting. We also have baselines such as relay SGD, QG DSGD-M, and DSGD. We also present the results for QG DSGD-M with naive knowledge distillation and also our method, which is QG IDKD. Clearly, we see that IDKD performs best among all the decentralized techniques. Here we present the results of IDKD as a function of skew. So we visualize this as a graph with the baseline in black and IDKD in gold. Firstly, we see that as Q increases, that is left to right, the performance goes down, both for the baseline and IDKD. However, we see that as Q goes up, the performance gap between IDKD and our baseline also increases. This IDKD is better suited to handle higher skew data. Similarly, here we plot the performance of IDKD on different topologies. So here, instead of ring, we choose the social graph. And again, we see that IDKD improves performance. On the left is QG DSGD-MN, which is our baseline, and on the right is QG IDKD. Clearly, both on CFAR 10 and CFAR 100, represented in gold and black, the performance goes up, showing that IDKD is not only able to handle ring topologies, but also other topologies such as social graphs. Here we visualize pre and post IDKD data distribution. Specifically, we want to see how the number of samples per class changes before and after IDKD. We visualize the normalized class distribution pre and post IDKD from a single node of a 16-node ring graph. This was done on CFAR 10 dataset with skew alpha equal to 0.1, where IDKD used TinyImageNet as the public dataset. Pre-IDKD is visualized in orange and post-IDKD class counts are visualized in blue. We can clearly see before IDKD, there's a heavy skew for classes 7, 0, 1. But after IDKD, the class distribution is more uniform. Understand how each component of IDKD affects performance. IDKD has two components, knowledge distillation and OOD detector. Knowledge distillation is denoted as KD and OOD detector as OOD. We show the baseline algorithm QG DSGD-MN in green. Then we have baseline plus KD in orange. Baseline plus KD and the OOD detector, which is nothing but IDKD, is shown in red. Also, as a comparison, we also pre-train the model on the public dataset and then use the baseline algorithm and is shown in blue. Clearly, we see how each component improves performance. KD improves over baseline for CFAR 10, but we don't see the same thing on CFAR 100. But KD with OOD improves performance. One of the big advantages of decentralized learning is robustness to node failures. Node failures result in time-varying graphs. To study this aspect, we introduce random communication failures at the rate of 1 and 2%. We evaluated DSGD and SGP because they are known to converge under time-varying graphs. We see that IDKD improves DSGD's performance via data homogenization even under node failures. Interestingly, at 1 and 2% communication failure rates, we see that these disruptions act as a form of regularization, boosting the baseline DSGD performance. We visualize the performance of IDKD under node failures. Here we show two graphs for 1% and 2% failure on left and right respectively. We obtained the results on CFAR 10, CFAR 100 ImageNet when using an alpha of 0.05 on an 8-node ring network topology. Here we visualize DSGD, our baseline algorithm, in yellow, and DSGD IDKD in orange. Clearly, we see IDKD improves performance of DSGD. We also have SGP, another algorithm known to converge under time-varying graphs, as reference. We briefly discuss the compute overhead and scalability of IDKD. We evaluated IDKD's performance as the number of node increases, specifically for 8, 16, 32, and 64 nodes in a ring topology. What we saw is that as the number of nodes increase, the performance decreases. This is also true for baseline algorithms. This is due to the fact that as the number of nodes increase in a ring topology, the speed of information travel reduces. Despite the drop in performance, IDKD consistently outperforms other techniques, demonstrating good scalability. We also evaluated IDKD's compute overhead, and we see that IDKD incurs about 1.5% to 15% compute overhead compared to the baseline algorithm. On average, it's about 4.5%. In conclusion, we present a solution to handle non-IID data distribution in a decentralized setting. The proposed IDKD solution handles non-IID data through knowledge distillation. It homogenizes the data distribution by aggregating distilled labels on a public dataset. IDKD outperforms knowledge distillation by up to 13%. It achieves up to 8% improvement over state-of-the-art techniques on non-IID data. It achieves these improvements while maintaining minimal communication overhead. We also see that it's robust to node failures. You can find more details in our paper linked below along with the code. Thank you.